Hello, hello, and welcome back to CS500 Design and Analysis of Algorithms. We are currently discussing Chapter 4 about amortized analysis. And the gist of amortized analysis to consider the total cost, the total worst case cost, if you like, of a sequence of operations. Like the user makes a sequence of calls to the data structure, to the data type we're analyzing. And in amortized analysis, one adds up all the costs of all the individual calls and then divides that total cost by the number of calls. So this is kind of an average, but it's not average over all possible inputs, but it's average over all possible sequence of calls. And the sequence of calls is made by the user, and we analyze the total cost of a worst case such sequence of length n, and then divide that total cost by n. Once we have analyzed the amortized cost of such a data type, then we can apply that. So when we analyze a more advanced algorithm that uses that data type, that says, for example, Prim's algorithm for a minimum spanning tree. Prim's algorithm for minimum spanning tree builds on top of a priority queue data type. And in CS300, we have considered a simple implementation of a priority queue with polynomial cost, polynomial running time in the worst case, and thus we concluded that Prim's algorithm for minimum spanning tree also has a polynomial cost. But here, in this advanced course, CS500, we have analyzed the amortized cost of an advanced data type, of an advanced implementation of a priority queue, namely of the Fibonacci heap. And in the Fibonacci heap, we saw that most operations have constant amortized cost, and only one operation has logarithmic amortized cost, which means that whenever the user makes a sequence of calls to Fibonacci heap operations, to the Fibonacci heap as a priority queue, then the total cost is the amortized cost times the length of the operation. So when the user makes a sequence of calls to extract min, then the total cost is the number of calls times the amortized cost of extract min. When the user makes a sequence of calls to decrease key, then the total cost is the number of calls times the amortized cost of decrease key. And we saw that the amortized cost of decrease key is logarithmic, and the amortized cost of extract min is actually constant. And that gave rise to the improved cost. And now we're back to worst case cost. Then we have Prim's algorithm based on the amortized analysis of the Fibonacci heap. And then we proceeded to analyze another algorithm for minimum spanning tree, namely Kruskal's algorithm. And this is where we resume the lecture right now. So let me start by sharing the slide. So here you see recap of Kruskal's algorithm for minimum spanning tree, classical algorithm that we already discussed in TS300. But now we want to look at it from the perspective of amortized analysis of the underlying data type. And the underlying data type is a disjoint-set data type. So here you see Kruskal's algorithm. Remember that Kruskal's algorithm maintains a collection of forest of trees and then repeatedly joins two trees the two trees that are connected by the least weight edge. So Kruskal's algorithm must repeatedly um, um, find the least edge. So this can be done after sorting all the edge weights, and then takes the two trees in its forest that pertain to the endpoints of that edge. So whenever that edge is within a tree, then we can discard it, because then it would add a cycle, and cycles are both redundant and also violate the tree property. So any edge that is within a tree gets discarded right away, whereas any edge that connects two previously disjoint trees will be added and thus connect the two trees, and thus result in the two trees being replaced by their union. So these are the two operations that underlie Kruskal's algorithm. So here you see an example run, but we already had that last time. And here you see a pseudocode. And in the pseudocode, you see the underlying data type, namely a disjoint set data type. Data type that maintains a collection of disjoint trees. And whenever we want to add an edge, as in this case, if two edges do not belong to the same subset, to the same tree, then that edge gets added to the final collection of edges, resulting finally in a single tree. The forest gradually boils down to a single tree, and we add that edge and we join the two trees, which corresponds to the union operation of the collection of edges of the first tree with the collection of edges of the second tree. And in order to do that, our data type must support the union operation, union of two disjoint sets, and to find out whether two nodes belong to the same tree or not, belong to the same set or not, we build on the data type supporting a find set operation. Namely, given two nodes, give me a handle, a unique handle of the set which the first node belongs to, and of the set which the second node belongs to. And by comparing the handles, Kruskal is then able to determine whether the two nodes belong to the same subset, to the same tree, or to different disjoint subsets to different trees. So these are the operations that we need for Kruskal's algorithm. And we've also already analyzed how often these operations are invoked. And particularly, we want to find out which operation is more frequent and which operation is less frequent, because the operation that is more frequent should be cheaper in amortized cost. Repeatedly invoked means amortized cost. And the operation that is invoked less frequently may have slightly larger amortized cost, because that is compensated for being higher amortized cost is compensated by being invoked less frequently. We also have the make set operation, but that's also only relevant initially when creating singleton sets, when creating trivial singleton trees. So that's what we're going to analyze, and we're going to design a disjoint set data structure, implementation of the disjoint set data type that actually turns out to have amortized cost, which is given by inverse Ackermann function, one of the slowest possible, slowest growing functions we have in computer science. So here is the result that we're going to design and analyze the amortized cost of a disjoint set data structure with amortized cost alpha of m, alpha denoting the inverse Ackermann function, and it's such a slowly growing function that it grows even more slowly than the log star function. That's our plan for today. And just for comparison, Prim's algorithm with a Fibonacci heap, which is a competitor to Kruskal's algorithm with a disjoint-set data structure, had a total cost of m plus n log n. So, and we're going to improve that, and our improvement is better than Prim with Fibonacci heap whenever the number m of edges is between n, that's the smallest number of edges that a connected graph can have, and n log n. So in this range, we're going to improve. And we also started discussing the inverse Ackermann function as part of a collection of slowly growing function and their dual fast growing function. They're kind of pairs, they're antipodes to the same thing. To every fast growing function corresponds a slow growing function, namely its inverse. And to every slow growing function corresponds a fast growing function, namely its inverse. Well, I'm gonna have to say half inverse because a particular slow growing function, of course, will not and cannot be injective as functions from integers to integers. As functions from real to reals, the logarithmic function is of course injective and has as its inverse the exponential function. However, as functions from natural numbers to natural numbers, we need to round up or down, and thus that destroys injectivity. So the integer logarithm is not an injective function, therefore does not have an inverse in the strict sense. But when we round up or down, then we can have this pairing, the duality. And we saw examples of that duality between the integer exponential function and the integer logarithmic function rounded up. Namely, it's least n such that the exponential of that n becomes greater or equal to the given argument capital N. So here you see what I mean with inverse, namely the exponential function arises here, and we need to take the minimum because it's not injective. And then the next level, we consider the double exponential, even faster growing function. And conversely, its inverse, rounded up, is the log function, which is even more slowly growing. And yeah, again, it's in the inverse in the sense that here the double exponential arises. And then we proceeded even further up, triple exponential, quadruple exponential, and on the other end of the spectrum, triple logarithm, quadruple logarithm, and finally, tower. Tower means exponential, only of twos, but the height is now not constant, but the height varies. So exponential has single height, double exponential has height 2, triple exponential has height 3, and so on. And tower has height n, not constant, but the argument determines the height. Now that's a really fast growing function. It grows faster than any exponential, faster than double exponential, triple, quadruple, and so on. And the inverse of the tower function, which is also called tetration, here you see an inductive definition of tetration, 2 tetration n, tower of height n is a tower of height n minus 1 on top of an exponential to 2, right? So that's an inductive definition of tower of a tetration, fast growing function, and on the opposite end there's the corresponding slowly growing function, the so-called log star function. So log star means how often can we apply the binary logarithm length 1 to the argument before the argument becomes less or equal to 1. And again, this is the inverse of the tau function, fast-growing, slow function. And we ended with last time with a quiz to give you an impression of how slowly growing the log-slow function is. And you were right. So this is an inductive definition of the log-slow function. And we talked and we ended with a quiz where you were asked to calculate the logarithm, the double logarithm, and the log-slow of some really, really large numbers. I mean, 2 to the 64, that's the number of configurations that your computer memory can have, right? So then 2 to the 128, that's even more, that's the square of that. And 2 to the 512, that's more than the number of atoms or electrons, far more than the number of atoms and electrons in the universe. So that number never even can ever even arise even remotely. And still the log star of that was what, like 5 or so, right? So that was to give you to train you to practice operating with slow growing function, and also to give you an impression how slowly growing these functions are. They grow so slowly that even when applied to the number of particles in the universe, they still are only like 5. So for all practical purposes, they can be considered like constant, but of course, from our theoretical asymptotic perspective, they are not constant. They do grow just very slowly, even more slowly than log. And that was the preparation to an even more slowly growing function, named the inverse Ackermann function. And again, the inverse Ackermann function is the inverse of an even faster growing function. So what is the faster growing function? That's the Ackermann function. So just a bit of historical context. Ackermann was a German mathematician, a German logician. He did his PhD thesis under David Hilbert, the famous David Hilbert. And after completing his PhD thesis, he wrote a book with Hilbert. Well, to be fair, he wrote a book. Hilbert had supplied the material. Hilbert had taught lectures on logic, the first lectures on logic ever, an entire lecture series, 22 lectures. And Ackermann helped Hilbert turn that lecture series into a textbook. Hilbert was already pretty old at that time. Well, he was 60. Hilbert lived until the age of 80, but he really needed and relied on the assistance of the then fresh graduated Ackermann, freshly graduated from a PhD. And so that was Ackermann's important contribution. And after that, Ackermann decided to get married and to raise a family. And actually, that annoyed David Hilbert. Hilbert became annoyed with Ackermann wanting to get married and raise a family. Maybe one reason was because David Hilbert's only son had to be hospitalized for mental illness, and maybe there was some envy underlying. But long story short, David Hilbert was the most powerful and influential figure in mathematics, in logic at that time, and he decided to punish Ackermann for wanting to raise a family, and he result, Ackermann had to become a high school teacher of mathematics because of David Hilbert's punishment for Ackermann wanting to raise a family. But actually, Ackermann became a very good high school teacher in mathematics, and you know, the as multiplier, the impact factor of math teachers is much, much higher than that of scientific logicians. So Ackermann had a very successful and happy remaining life in spite of Hilbert's score. And also, I leave it to you to judge David Hilbert's behavior. But now, resuming to mathematics, Ackermann defined the function that we nowadays call Ackermann function. Actually, he defined a sequence of functions, and the basic of that sequence of functions is the increment function. And you may recall from elementary school, repeatedly incrementing, that's basically adding, right? So you can consider adding as repeatedly incrementing. And multiplying two integers means repeatedly adding, right? So if you multiply 5 times 7, it means you add 7 plus 7 plus 7 plus 7, 4 times, repeatedly adding. Now, what is repeatedly multiplying? That's, of course, the exponential function. Like 7 to the 4th means 7 times 7 times 7 times 7. So all the basic arithmetic operations that you know from elementary school are basically part of a hierarchy. Each one, the next level, repeatedly applying the previous level. Addition being repeatedly increment, multiplication being repeatedly adding, exponential function being repeatedly multiplying. And what is repeatedly multiplying? Well, that's tau, right? So exactly what we talk about here, right? Repeatedly taking exponential, that's a tau function, the tetration. And now what is the next level up of? Well, the next level is repeatedly tetrating, repeatedly towering. And Ackermann formalized this idea into his sequence of functions. Small technical detail, he did not consider increment as basis, but he considered double increment, adding 2, as we now call, twice incrementing as the base function. So the zeroth ground level Ackermann function is incrementing twice instead of once. That's just a technical detail. I'm not going to expand on the reason. And then repeatedly adding, repeatedly incrementing is adding, repeatedly adding is multiplying, and so on. And Ackermann combined all this into one inductive definition, namely the next level applied to n plus 1 is taking the previous level and applying that to n. So that's the basic idea. And maybe I'm going to make an assignment about you spelling out the first few levels of Ackermann's function. No, I think we have that here in the slide. So for example, the first level of the Ackermann function is adding it to itself. So multiplying by twice, adding to itself. And again, we have here technical detail and adding 3. So base level, zeroth level is incrementing twice. Next level is adding to itself plus something. Next level is, remember, repeatedly multiplying. So namely n times multiplying to itself, that's the exponential function. And there's some technical things, +3, -3 here. Next level is the tetration, essentially. And the next level is repeatedly tetrating, but that doesn't even have a name yet. That's just the 4th level of Ackermann's function, is repeatedly tetrating, and so on. So in this sense, Ackermann combined all the basic arithmetic functions into the basic ground level of a hierarchy. hierarchy that extends to towers, tetragration, and beyond. So this is a family of fast and faster growing function. The higher the level, the faster it grows, right? Immediately obvious. There's also induction start that we of course need, that's here. So long story short, Ackermann's function is actually a family of functions that grow faster and faster. The next level grows even faster than the previous one. And now we're going to kick in the booster, and then we will turn that into one single function that grows faster than all other functions in the Ackermann's hierarchy. Namely, we make a diagonal. So here we have fixed the level. So that's the first level, second level Ackermann function, third level Ackermann function on argument n. And diagonal means we're now going to consider the nth level Ackermann function on argument n. So now both grow, the argument and simultaneously the level also grows. And you can imagine how fast growing a function that is, right? So we kind of gear up both parts, the level and the argument. Now that's a function of only one argument, and it grows faster than any fixed level in Ackermann's hierarchy. That's a high, fast-growing function. And now we switch perspective again and take the inverse of that incredibly fast-growing function, growing faster than titration, everything else. What is the inverse? Do the same. So here you see the diagonal Ackermann function, nth level, and argument n. That's the fastest growing computable function, total function, recursive function. And now we take the inverse, the least argument that makes that exceed the capital N. And that's the inverse Ackermann function. And if you have realized how fast this diagonal Ackermann function grows, then that means that the inverse Ackermann function grows extremely slowly, and particularly it grows slower than logarithm, it grows slower than log, and it grows slower than log star. Since the diagonal Ackermann function grows faster than titration, therefore its inverse goes slower than log star. And that's what we're talking about. That's the amortized cost of a data type and data structure that we're going to analyze. We're going to analyze the amortized cost of so-called union find data structures, and we're going to see that the amortized cost is the inverse Ackermann function. So I hope that is impressing you very much. Recall that for practical purposes already the log star function is basically constant. The inverse Ackermann function is even smaller than that. So that's all what we want to do today. So what is a disjoint-set data structure? Disjoint-set data structure supports three operations: make set, find set, and union. And to give you, instead of a formal specification, I want to convey the intuition behind that. And that intuition, we're going to give you some example visual illustration. So make set, union, and find set. So make set, X makes a singleton set with the element X. So here you see the element X, that's a black dot, and the blue circle, that's a set, and it's a singleton, so there's only one black dot inside it. And let's suppose the user calls another make set, and many make sets, which means that now our data type stores many singletons, as you see here. And next, the user calls a union operation. Union of these two sets result in them being combined into one larger set, a two-element set, right? And now the singleton sets are not present anymore. They have been replaced by this larger set. So that's an important aspect of this data type that once we call the union operation, the individual sets are discarded and replaced by the union of the two sets. Right. So that is the union operation, and consider another union operation for the sake of an example. Right, so second. Yes. So another union operation and another union operation. And the union operation of two previously unioned operations results in even larger set, and so on. And one subtle point about this union operation is the union operation receives as arguments not sets, but handles to sets. So the union operation, for example, here says union of this and union of this. So x and y are here points, not sets. Okay, so this point and this point represent this set and this set. This point also represents this set. This point represents this set, and this point also represents this set. So this raises the question of how can we check whether 2 points represent the same set. This point represents a different set. This point represents a set different from that. And this is where the find operation comes into account. So here we have continued our sequence of union operations. Now comes the find set operation. The find set operation receives as argument an element, a black point, and returns a unique black point in that set. So let me say that again. Let's say this one is the unique representative of this large set. So that means that find set called with this argument would return this point. Find set when called with this argument would also return this point. So any argument x of any element in this large set would always return the same point as a unique representative, as a handle. And this will allow the user to compare sets, to check whether 2 points belong to the same set. These 2 points belong to the same set, whereas these 2 points belong to different sets. And this can be compared by first calling find set, tell me unique handle of this set, tell me the unique handle of this set. Since the unique handles, this point and this point, are different, that means these 2 points belong to different set. That's the importance and relevance of find set. Return a unique handle of the set. It doesn't change anything inside the data structure. It only returns a unique handle so that the user can compare sets. So let's say for the sake of some example, the gray points are the unique handles of these sets. Now, how can we implement this data type, right? So data type is abstract, and we want to implement that, and we want to implement that efficiently. We want to implement that with efficient worst case first, and then we're going to aim for an even more efficient amortized cost implementation of this disjoint disjoint set data type. So that's our plan for now. And just to give you motivation, recall that this disjoint set data type is exactly what Kruskal builds on, what Kruskal needs. When Kruskal repeatedly calls union, that's exactly this union. When Kruskal initially repeatedly calls find set to see whether the 2 points x, u and v belong to the same subset or not. That means calling find set for both of them and check whether the returned handles coincide or not. Also, Kruskal initially calls make set for every single vertex in the input graph. We've already discussed that. So this is really what Kruskal's algorithm efficiency based on. So let's first talk about a naive implementation of a disjoint set data structure using a graph, using a pointer data structure, namely as a forest of depth 1. Forest means collection of trees, and depth 1 means every tree is just one node, the root, one root, together with all its children immediately attached. So there is no secondary um, um, descendant, only root and children, no grandchildren. So here you can see an example. So here we have the root serving as the unique handle, and all children point to the root. So that means we can uh, realize the find set operation in constant cost, namely when given a point, we simply follow the pointer to the root and return the root as a handle. So that's just one pointer to follow because we only have children, no grandchildren. So that means we can do that in constant cost. And same here, whenever a user wants to find set, given this argument, our implementation follows the one pointer to the root and then returns the root as handle. So that means find set has constant cost because we're talking about depth 1. If we were talking about more general trees, of course, then following all the path up from the leaves to the root would have non-constant cost. So that's where the depth 1 comes into account. On the other hand, maintaining that during the union operation is more costly, right? So now let's suppose that the user wants us to make the union between this set and this singleton. Then we need to change pointers, right? And one way of changing that after union is to make that the new unique handle, the new root of a tree of depth 1, which requires redirecting all pointers to this new root. All pointers change and switch here. So that's all pointers directing here. And that's costly, right? That's cost as large as the set is. Well, to be fair, which set? Yeah, you already see that this seems like a stupid idea to make this a new root. It seems more efficient to keep this root and add only one pointer from this set to here. Or more generally speaking, let's keep the larger set root, the larger set's handle, and redirect all pointers from the smaller set in the union operation. That seems more efficient, at least as a heuristic and from terms of constant factors. Of course, if both sets have roughly the same size, then there's not much benefit, right? So this seems like just a heuristic. Let me say the heuristic. So first, if we alternatingly call make set and union, then this naive implementation can have a total worst case running time of n squared, meaning that the amortized cost is n linear amortized cost. This is far larger than what we're aiming for, right? We're aiming for log star amortized cost, or even for alpha amortized cost inverse Ackermann function. But this first implementation has linear amortized cost, which is exceeding, but this is our starting point for our meta loop, starting, designing, and analyzing algorithm, and then trying again, more efficient algorithm, and then trying again, even more repeatedly. So this is our start. And now we're going to um, look at our improved algorithm, and we're going to analyze the improved algorithm that I already mentioned before, namely the union by weight heuristic, namely attach the smaller tree to the larger tree. So that's not what we did here. Here we attached the larger tree to the smaller tree, which required updating and changing so many pointers, because all pointers in the larger tree would then need to change direction to the root of the smaller tree. Whereas if we follow this heuristic, attaching the smaller tree to the larger tree seems more beneficial and more efficient. So that's what we try here. And initially, this is just a heuristic, right? And as I said, if both trees have roughly the same size, then there doesn't seem to be much of a benefit because ties are broken equally here if they both have the same size. But it turns out that we can analyze that rigorously, and that the analysis already gives a considerable boost in amortized cost from linear amortized cost to logarithmic amortized cost. So theorem, the union by weight heuristic yields a total time of m plus n log n for any sequence of n calls to make z and m calls to find z and union. So let's look at this for a moment for the statement, just to understand the statement. So in this statement, we're actually considering amortized analysis. Maybe you don't see it here yet because it refers to total time. But now let's divide that total time by capital M. Capital M. No, let's divide it by capital N. And observe that capital N is always at least as large as capital M, because we can call find union only as many times as there are sets. After we have called union n times, then all the sets have been merged to one single remaining set. So M is kind of the important here. M is what dominates the length of sequence of calls, right? So here technically the length of the sequence of calls is n plus m. So we should divide everything by n plus m, the length of the sequence of calls. But it suffices to divide by m because that's what dominating things asymptotically. And when you do that, we see that this part becomes constant after the division. And here this part cancels after the division, resulting in only logarithmic amortized costs. And that's a first huge improvement. And now we take a short break for you to digest that and to ask questions. And then we're going to prove this theorem. So this is a short break for now. Okay, thank you very much for your questions and for the opportunity to clarify some points. And now, as promised, we're moving on to prove this theorem, stating that the simple union by weight heuristic results in an amortized logarithmic cost for the disjoint set data structure. So that's what we want to do now. And for the purpose of analysis, let's consider this example where we have one tree of height 1, right? And let's suppose Right. So find set, as we saw, is already constant cost, worst case cost. Make set is also constant cost. So the important thing to ask about is really the cost of union, more precisely the cost of a sequence of calls to union, right? So amortized analysis, we only consider sequence of calls, and the calls that really matter here is a sequence of calls to union. So here we start with 1 tree of height 1, and now let's see, when does a pointer from node X get updated from its previous handle, its previous root, to a new root. And that can happen only, right? So here you see that pointer from X gets updated. That can happen only when it gets updated to the root of a set which has at least the same size as the previous set, right? Because that's the essence of the union by weight heuristic. We only update the pointers in a smaller set to point to the root of the larger set. So whenever a pointer gets updated, there must be a larger set or at least a set of same size. So for X, pointer from X to get updated, which is what makes the cost, we're analyzing the cost. We're counting how often a pointer gets updated during a sequence of call to union. And for pointer to get updated, there must be another set of at least the same size as the set where the element originally belonged to. So that's what you see here. A node's link gets updated only when its set is combined, call to union, with another set of larger or at least equal size. So that's what you see here. Whenever a pointer gets updated, there must be another set of at least equal size. So that's for one update. And after that update, after that union, that means we have the user has made us create the union of two sets of equal size, resulting in one set, right? So the previous sets get replaced now by the union, which is one set of twice the size. So the size must have doubled whenever a pointer gets updated. The size of the set that the pointer belongs to is doubled. Now, when can the pointer get updated again a second time? For that to happen, there must be another set of equal size, but now the other set must have double the size of the original set, right? Because now, after the first update, the pointer belongs to a set of twice the size, and for it to get updated a second time, and that means we arrive at a set of already 4 times the size. And for the pointer to get updated a third time, that means there's a set of 8 times the size. So whenever the pointer gets updated, that means the size of the set it belongs to gets doubled. And that means conversely, we must have a very large number of points for the elements for a pointer to be able to get updated repeatedly. So an update, one pointer can update it once, only when there's a set of double the size. Pointer can be updated a second time when there's a set of 4 times the size. And the pointer can be updated k times only when there's a set of size 2 to the k in the result. And for a set of size 2 to the k to be in the result, we need to have at least 2 to the k elements. And to have 2 to the k elements requires that the user previously has made 2 to the k calls to make that in order to create that many points initially. So that's an important observation, that so many updates, k updates, can only occur after so many calls to make set. And that means conversely that the number of updates can be at most logarithmic in the number of calls to make set. We call that n denotes the number of calls to make set. So any pointer can be updated at most log n times by taking the logarithm of both sides here. That's important. That's what proves this, right? Namely, we already analyzed cost of make set is constant, cost of find set is constant, and cost of union, amortized cost, can be for every point, each of the n points, update can occur at most log n times. So whenever there are n points, the total cost of updates, the total number of updates can be only at most n log n for n points, each one at most log n times. So the total cost of a sequence of u calls to union can be at most n log n. That's very interesting, right? That's very surprising. And that's our first analysis of a first improved union disjoint set data structure with a simple heuristic, which we have now actually analyzed. So it's not a heuristic anymore, it's an algorithm. And we saw that the total cost at m plus n log n, which means that the amortized cost is log n, or better than n in our first example, but still far away from what we're heading at. We want to have disjoint set data structure with amortized cost log star n, not log n, not log log n, not log 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 n, but log star n, and even smaller inverse Ackermann of n. That's our goal. But I see that we're running out of time, and this is the last lecture before the midterm exam. So let me stop here and just with a cliffhanger and announcing that after the midterm, we're going to resume this chapter and conclude this chapter by analyzing the lazy union by rank heuristics, which turns out to have amortized cost inverse Ackermann function.